Hello and welcome. Today we are going to talk a little bit about using block diagrams for analysis of process systems. What is a block diagram? It is a graphical representation of a system of equations. And to set things rolling, let's look at a very simple single equation, z is equal to x plus y. This can be represented graphically as shown here, where you have this summation block. The summation block sums the inputs and outputs the summed inputs. So here's your output, these are your inputs. Yeah, so it's a very simple graphical representation of the same equation. Now let's take a system of equations, and the system of equations is here. Z is equal to k1y plus w, y is k2x minus v, and x is k3z plus u. So now let's make a graphical representation of these equations, or make a block diagram corresponding to these equations. So let's look at the first equation. First equation is basically saying z is equal to k1y plus w. So z is equal to k1 times y. So this signal is k1y and this signal is w. You add the two, so therefore z turns out to be k1y plus w. Now the second equation, y is equal to k2x minus v. So y is equal to, this signal is k2x, and I have the v signal, I multiply it by minus 1, so this signal is minus v. When I sum these two signals, I get y is equal to k2x minus v. And then x is k3z plus u. So I already have z here. So this signal is k3z and this signal is u. When you add the two, x becomes equal to k3z plus u. So you can see this is the block diagram representation of this three sets of equations, and immediately you can see that there is a feedback loop in there. So that's the advantage of block diagrams. You can see the flow of information very clearly, and particularly the presence or absence of feedback loops, interactions, what affects what, the flow of causes and effects. That becomes very clear in a block diagram compared to a system of equations. So a block diagram clearly reveals the information flow, in particular the causes and the effects, their cascades. It also reveals the presence or absence of feedback loops, if any. And why are feedback loops important? Feedback loops are important because feedback can cause instability. And just to show you this, I've just discretized the system of equations by putting an index I. And now, so let us just think of this system as u, v and w being causal inputs, these being inputs to the system. X, y and z being system states that evolve in time due to changes in the inputs. And the way we are going to think about this block diagram is, you give an input change and wait for some time for the system to settle at its final value, and one can think of this as, and once it has settled at the final value, this is input or closed again. So this switch closes and opens every sampling instant. Let us just think of it like this. So let's just see how the system states evolve if, for example, delta u changes. So here's the evolution, and maybe I should do it first and then put on that table. Okay, so if delta u, initially everything is at 0. If delta u at instant 0 goes to, let's say, unit step goes to 1, then this guy is 0, this guy is 1, so this guy would be 1, this guy would be k2 times 1, v is 0, so it doesn't really matter, so this guy would be k2 times k2, this guy would be k1 k2, w is 0, so it doesn't really matter. So z will go after one iteration to k1 k2, and this signal will go to k1 k2 k3. Okay, so basically when I execute it for the first time, when I execute these equations for the first time, delta y is k1 k2, oh sorry, delta z is k1 k2. Maybe I should do it differently. So delta x at the first instant is 0, and delta z is k1 k2. Then at the second instant, when I execute it, delta x goes to k1 k2 k3. Of course this is 0, and if I go forward, the change in z because of this change in z, therefore this signal will go to 1 plus k1 k2 k3, and because of this extra change, this guy will change by k1 k2 times k1 k2 k3. So this guy will become the extra change because of this change in the feedback signal, k1 k2 square times k3, and therefore this signal will become an additional correction to this signal, will be k1 k2 k3 whole square, and therefore at instant 3, no change in u, this guy is going to be k1 k2 k3 whole square, and therefore this guy is going to be k1 k2 whole cube times k3 square. And because of this additional change in the feedback signal, at instant 4 you can calculate, and so on and so forth. After n instants, or after n such instants, you can see that delta z is going to be the incremental change in z because of the feedback is going to be k1 k2 to the power n times k3 to the power n minus 1. So if I look at the total change in z, total change, not every instant but the final value that z reaches, that's going to be the superposition or the sum of all these incremental effects, and that's going to be k1 k2. If I take k1 k2 common, it's going to be 1 plus k1 k2 k3 plus k1 k2 k3 to the power 2 plus k1 k2 k3 to the power n minus 1. And this sum is going to be, I think if you use geometric progressions, it's going to be k1 k2 times 1 minus k1 k2 k3 to the power n divided by 1 minus k1 zn, sorry, k2 k3. And if n tends to infinity and if k1 k2 k3 is less than 1, then this progression converges. If it is greater than 1, you can see that this progression will go to infinity. Z will keep blowing up for k1 k2 k3 greater than 1. For k1 k2 k3 less than 1, it will settle at some value where this is the index I. And this value that it settles at is going to be k1 k2 divided by 1 minus k1 k2 k3, because as n goes to infinity, k1 k2 k3 which is less than 1, this will go to 0 as n goes to infinity if k1 k2 k3 is less than 1. So you got to explicitly state k1 k2 k3 less than 1. Okay, so you can see that if k1 k2 k3 is greater than 1, because of the feedback, the secondary effects introduced by feedback, you can have instability. On the other hand, if k1 k2 k3 is less than 1, you get a stable response in the sense that z settles at a finite bounded value, and this is that finite bounded value. So this was a very simple illustration of instability due to feedback, and that's exactly what I was trying to say. And the sum of the n terms is going to be a geometric progression as shown there with ratio k1 k2 k3, and for n going to infinity, z blows up if k1 k2 k3 is greater than 1. It is bounded if k1 k2 k3 is less than 1, and this bounded value, that means if the series converges, is k1 k2 divided by 1 minus k1 k2 k3, and this is a very simple illustration of the possibility of instability due to feedback. Okay. Now, because block diagrams reveal the presence of these feedback loops, and feedback loops can cause instability, it is very good to have these block diagrams in front of us so that if there are any feedback loops, it captures our attention immediately, and we do the necessary analysis to show that to ensure that the system is stable. This is particularly relevant for feedback control loops, because there the control is based on feedback of the output that we wish to control. So here is a very simple block diagram, and in this block diagram, output y is equal to, this guy is GDD and this guy is GPU, and therefore the output y is GPU plus GDD as stated here. Now let's say we apply a feedback loop. So we're going to say U is GC times E, GC times E, and E is Y set point minus Y. So E is summation of Y set point, and we are taking minus Y, so we are going to take the Y signal, multiply it by minus 1, and then shove this into my summation. That's what the block diagram would be if we want to implement this system of equations, which is actually a feedback control system with a disturbance and a control input to the process manipulated by a controller basing its manipulations on the error, which is the deviation of the process variable from its set point. Okay, so the block diagram looks something like this, and now what I'm interested in is, see, if you look at this system, let's look at this system. This is the system, that's the output that I'm interested in. This system has got two inputs. What are the two inputs? Y set point and disturbance T, and it's got an output. So now I want, obviously Y will get influenced by Y set point, Y will also get influenced by D, and what I want are transfer functions that relate the time evolution of Y with respect to Y set point, changes in the set point, and the time evolution of Y with respect to changes in the disturbance. That's what I want. So essentially what I'm looking for is an equivalent block diagram with Y and D as inputs to it, with D and Y set point as inputs to it. What goes in here? That's what I'm looking for. So what I'm looking for is fill in the blanks. How do we do the fill in the blanks? Well, it's actually quite simple. So let us say we want Y set point to Y, so we start from here. Y with respect to Y set point, so this is Y. Let's start going back from Y. This is going to be GP. So Y is equal to GP times U, and U is GC times E. U is GC times E, and E is Y set point minus Y, and E is Y set point minus Y. And collect the Y terms on one side, and therefore what I get is 1 plus GCGP. By the way, all of this is in the Laplace domain. I am just dropping the subscript S, is equal to GP GC Y set point. Therefore what we get is Y upon Y set point, the transfer function, is equal to GCGP divided by 1 plus and this transfer function is the evolution is for the time is for the evolution of y if y set point changes. So this is actually the servo transfer function. I'll call it G servo. So what should go in here should be similarly hang on. I think I should write it now. GCGP similarly let's look at what happens to y if d changes. So if d changes, then we'll say y set point is 0. Y is equal to GD times D plus this guy, this guy, which is actually GC GP times y set point minus y, but y set point is 0 and therefore y over d becomes GD over 1 plus GC GP, and this is G regulator because this transfer function relates the output to the disturbance. So this is the regulator response transfer function. So what should go in here should be so this is how we solve block diagrams. It's essentially algebra. We just derived this, and in equation form this is what we have. This is the servo transfer function, this is the regulator transfer function. Notice that the denominator polynomial in both the transfer functions servo and regulator is the same, which is 1 plus GPGC, and we know that denominator polynomial in a transfer function when it is set to 0 is the characteristic equation of the system under consideration. What is the system under consideration? The system under consideration is this entire guy with the feedback loop in there. So the closed loop characteristic equation is this guy. The roots of this equation are the roots of the closed loop characteristic equation for the dynamic system in the block diagram shown. Okay, that's the next thing that is important, that needs to be noted, and we'll be working with this a lot subsequently. Now, to simplify the algebra, can we come up with a rule that allows us to, so the rule is very simple. So let's say we are looking at the disturbance to y transfer function, which is this guy. How do we get this? This is the input, this is the output. I go in the forward path from the input to the output. The transfer functions that I encounter, there's only one transfer function that I encounter, that is GD. That goes in the numerator. And then I go around the entire feedback path, what are the transfer functions that I encounter? I encounter GC times GP times minus 1 1 minus this 1 minus whatever you encounter in the feedback path. So this guy turns out to be 1 plus GC GP, and you can see that's the denominator right here. So the tentative rule that I am proposing for feedback loops is go from the input to the output. The numerator is going to be all the transfer functions in this input to output forward path. Denominator is going to be 1 minus the product of all the transfer functions that you encounter in the feedback path. Let's apply this rule over here for the servo transfer function. Let's see what happens there. So servo is relationship between y and y set point. So if I go along the forward path, that's actually GCGP. So the numerator is going to be GCGP. That looks okay. Denominator, let's go around the feedback path. Denominator is going to be 1 minus whatever we encounter in the feedback path. That's going to be GC GP times minus 1, which is again 1 plus GCGP or GPGC. So for simplifying feedback loops using block diagram algebra, if you will call that. So for simplifying block diagrams, resolving a feedback loop in a block diagram, the rule is as stated here. Numerator polynomial is the product of the transfer functions in the forward path from the input to the output, and denominator polynomial is 1 minus the product of the transfer functions in the feedback path. Let's do some simple examples. So now here I have two disturbances. It's a feedback loop with two disturbances: single input single output system, single controlled output, and single input to the process that can be manipulated. So what do I want? I want three relationships. What are those three relationships? Y by d1, y by d2, and y by y set point. So let's look at y by d1. So if I look at y by d1, what's in the forward path from the input to the output? GD1 GP. So y by d1 is going to be GD1 times GP divided by 1, because you got negative feedback, so it will be 1 plus GCGP or GPGC. What about this chap? Y to D2, it's going to be GD2 from here to here, and then whatever is in the feedback path, 1 plus GPGC. And what about the servo transfer function? It's the same as before. Whatever is in the forward path, that's GPGC divided by whatever is in the feedback path, 1 minus that, so that's going to be 1 plus GPGC. By the way, this rule can be, if the okay, so this, I mean, this is fine. If you look at the overall sense of the feedback loop, positive, positive, negative. So the overall feedback is actually negative. This is called negative feedback. Suppose I did not have this minus. If I did not have this minus, Then if I went around this loop, positive, positive, this would be a positive feedback loop. So when we are doing control, we are doing negative feedback. Positive feedback occurs in systems, for example, if you got recycle material or energy recycle, that's positive feedback. Okay. So for positive feedback loops, what occurs in the denominator is 1 minus product of. For negative feedback loops, 1 minus GPGC, for example, in this guy. For a negative feedback loop, it would be 1 plus GPGC. The negatives will actually change the sign. So for this particular example, this is what we get. So there's servo transfer function number 1, there's servo transfer function, there's regulator transfer function with respect to D1, there's the regulator transfer function with respect to D2, and that's that. Now let's look at example 2. This is something that you often see in model based controllers. This is the internal model control block diagram, and so if you look at this block diagram, this is the control input to the process. You have a model of the process. This is the actual process, this is the model of the process. GM is approximates GP, but it's not exactly equal to GP, so GM is approximately equal to GP. Okay, and the better the approximation, the better off the performance would be. So now what you do is, there is an unmeasured disturbance that's entering the process here, and this is a prediction of what the output should be. This would be Y predicted. This is actual Y, this is Y predicted, and if the model is good, if I subtract Y minus Y predicted, if the model is exact, then this is an estimate of the unmeasured disturbance. The hat is indicating estimate or from a model. So this disturbance estimate is fed back in a negative feedback loop to this controller, and this is the internal model controller control structure, block diagram structure. Question is, simplify this block diagram into a conventional feedback loop. So what is the equivalent simple feedback loop? What is a simple feedback loop? Simple feedback loop is, you got a bunch of transfer functions. So GP will of course be there. Simple feedback loop is actually, of course you cannot change the structure of the process, so disturbance will also be there. This is a simple feedback loop. What should go in here? That's the question. So if you look at this guy, well, so this is -1, this is -1, so this signal is actually positive feedback. Okay, so you can see that this guy is actually equivalent to, maybe I should just bring in the, this block diagram is the same as this block diagram, and we are just using the in addition and subtraction, the order of addition and subtraction is irrelevant. Add first, subtract later, subtract first, add later. I don't know, this is the associative commutative property of addition. So we are invoking the commutative property of addition and subtraction. A plus B is the same as B plus A minus B is the same as minus B plus A. Okay, so if you look at this signal, This signal is y set point plus, I'll call this u times, and I'm looking at this guy. Okay, so the contribution of this guy is y set point plus u times gm, and then of course there is this guy which is minus y. So I will do y sp minus y plus u times or gm times u. So this signal is y set point minus y, that's this guy, and then you're adding u times gm and you're getting this is, so this guy is y set point minus y plus gm times u, as it should be. So you can see that this and that, these two block diagrams are actually equivalent. And now we have everything in the way we wanted. This is a feedback loop. It's just that it's a positive feedback loop. Because it's a positive feedback loop, what are we going to get? This guy will get replaced by g star, whatever is in the forward path, divided by 1 minus whatever is in the feedback path, which is g star gm or gm g star. And so that's what we get here, where gc is this guy. This is equivalent to okay. With this brief introduction to block diagrams, let me summarize what we have seen in this lecture. The block diagram is a graphical representation of a system of equations. It clearly reveals information flow, cause and effect cascades, and in particular the presence or absence of feedback loops, whether positive feedback or negative feedback. And feedback loops may result in instability, and therefore it is important to look at block diagrams, because the feedback loop will immediately jump at us, whereas these feedback loops can get lost in a bunch of equations. A picture is worth 1,000 words, as they say. So a block diagram is that picture. Simplifying feedback loops, the rule is the numerator of the equivalent transfer function is the product of all the transfer functions in the forward path from the input to the output, and the denominator of the equivalent transfer function is 1 minus the product of all the transfer functions in the feedback path. One has to be careful about signs. In negative feedback loops, typically this will become positive because minus minus makes it positive. In positive feedback loops, it will remain minus. Often a mistake that gets made by all of us actually is that you've got a, let's say you got a, vy set point, you're summing all of, so this is a slightly different version, plus and minus, and let's say you got your controller, and let's say your GP has a negative gain. this has a negative gain. So for example, let's say GP is minus k times e to the power minus dead time s divided by tau s plus 1. Let us say this is GP as a transfer function, and for the time being we'll ignore the disturbance, and you got a feedback loop. You see, if GC uses the same sign, if KC is positive, what does that mean? That means the sense of feedback inside the loop is actually positive times negative times negative. So that's actually negative. That's actually positive feedback. You're not doing control. Control requires negative feedback. When you have positive feedback, this is the kind of response that you expect. You can also get this, but typically this is, if the feedback is too large, you'll get an exponential blow up. So one has to be cautious. So in this case, because the process gain is negative, Kc will have to be negative. And if this is negative, then the sense of the feedback is going to be negative times negative is positive. Then you go back around here and come here negative. So positive times negative is negative. So then this is negative feedback, and now you are doing control. And when you're doing control, so for example servo response, this is when you can expect this kind of a servo response. And of course, even in negative feedback, you could have that Kc is too large. If the feedback is too large, you do get oscillations, but then the oscillations tend to blow up. Yeah. So negative feedback systems will typically result in this oscillatory blow up kind of instability. Positive feedback systems will usually result in exponential blow up kind of. So this is a sign of positive feedback. And this is a sign of exponential blow up is a sign of negative feedback. Too much negative feedback. Okay, so one has to be very careful about signs when you're doing controls, because inadvertently you do not want to end up in a positive feedback loop. You must ensure that the overall sense of the feedback is negative. And this is what we do when we specify that a controller is direct acting or reverse acting. Direct acting corresponds to Kc negative. Reverse acting is Kc positive. Okay. The other thing that is of importance is that the seesaw closed loop characteristic equation is 1 plus GPGC is equal to 0. The roots of this equation are the roots of the closed loop characteristic equation. With this, we come to the end of this lecture. Thank you for your attention. Hope to see you next time. Thank you again, and goodbye.